and the topic of the talk is lifetime behavior of solutions to certain evolutionary problems. Many of us have met and know who, Professor Harsha, but to know each, if you don't know, we can reserve last few minutes to know each other after the question answer sessions. And the Professor Harsha, you will be having something like 50 minutes, 55 minutes, and then last 5 to 10 minutes will be reserved for the observations and things, right? And then
Okay,
last, and then after 13, if you have time, we can have some knowing each other, right?
got it.
Okay, so the floor is yours. Please go ahead,
Oh,
and I
thank
will
you.
be recording your talk.
Okay, thank you, Ravi. Thanks for this invitation. You had asked me some months ago, and I'm glad that I agreed. So here is the title. It's and you are able to hear me proper, right? If there is any trouble,
Yes.
you just let me know. The
Yeah.
title
Okay.
is Large Time Behavior of Solutions to Certain Evolutionary Problems. The way I have organized this talk is it's going to be very elementary. Basic knowledge of PDEs is sufficient, and it's more about you take a solution to an evolutionary problem and study its long time behavior. So essentially, this talk is about uh, solutions F to certain equation, partial derivative of f with respect to time equals to some operator, differential operator L acting on f. So you have a solution f to this problem, and you want to know what is the behavior of the solution when t becomes larger and larger. So that's the question we are interested in. And so we particularly ask this question: does there exist some equilibrium or steady state, f infinity? This is just a notation. So that equilibrium state is the one where only the operator vanishes on that function. L of f infinity is 0. So if there is such an equilibrium state, does this solution f, which is time independent, in the time going to infinity limit, does it converge to f infinity? Is the question. And if it converges, in what sense does it converge? In which norm does it converge? Okay, these are precise questions that we would like to address. And these are some standard questions, right, when you are studying evolution equations. In this talk, we will not be worried about the existence of solutions to these evolutionary problems. We are going to assume that there is a solution, and we are analyzing its last time behavior. Okay, so let's start with the simplest PDE that you can write. Okay, simplest to write. I am not claiming that.
Harsha,
Yes.
Rajesh wants to ask something.
Yeah, please.
Yeah, just one thing. So it's you don't assume linearity of the operator, right? No.
No, no, no. We will not be
Okay.
assuming any linearity here. We will
Okay.
be trying to understand this approach via examples. Okay.
Okay.
First
Yeah.
couple of examples are going to be linear, but then we will also take a nonlinear problem and address the same question. Any other question? There was a ping. I don't know. Shall I continue? Are you able to hear me?
Yes, continue.
Oh, okay. Thanks. So, so the first example that we consider is that of the transport equation. Okay, this is the simplest partial differential equation that we can write. I mean, I am not claiming that it is simple to solve or anything. It's just, it has got a function of two variables, and it has got partial derivative with respect to both these variables, first order. And this coefficient A is just positive, a real number. Okay, so you got this standard transport problem. You assign some initial data. This is a Cauchy problem, and we know that this is the solution to this problem. This initial data just being transported right along the characteristics. So u of t comma x is just a g, the initial data g evaluated at the point x minus 8. So this is the exact solution, and this solution to this problem also has got this conserved quantities. You raise this solution to any power, p integrate it over the x variable, it is actually equal to the initial data raised to the same power integrated in the x variable. So at first instance, you may be thinking, why are we looking at these conserved quantities? These conserved quantities help us decide what is the equilibrium state later on. Okay, but in this particular example, as you can guess, there is no equilibrium state for this problem. Like, by the way we define what f infinity was, you have to just act this operator. This is the L operator here is a times dx. So you act this on some function, it has to vanish. And such a function is a function which is independent of the x variable. And you are looking for time independent solutions. And so you are essentially looking for constants. But this constant, if you have certain conserved quantities in your equation, if your equation is conserving certain quantities, that property should kind of carry on to your equilibrium state as well. And this kind of conservation is not satisfied by your equilibrium state. That constant, if only possible candidates for the equilibrium state for this equation are the constants, and those constants, they do not satisfy these conserved quantities. And from here, you can say that there are no steady states for this problem, which kind of follows from this representation formula itself. This is a very convoluted way of saying that. But, just you look at this representation of solution that you have, because the information is just being transported, and there is no way this will converge to any equilibrium state. Okay, so this is one example, maybe a non-example of a problem which has not got any equilibrium state. So there is, the convergence doesn't make sense here. Okay, so next we will look at heat equation. So heat equation with Neumann boundary condition. So here we are going to confine ourselves to a smooth open bounded domain, omega. We are going to assume that its measure is 1. Okay, but if it's not 1, you can always take the corresponding measure to be dx upon the measure of the domain omega, so that actually you are looking for a probability measure on that domain. So without loss of generality, I am going to assume that the measure of omega is 1. Otherwise, you will be just working with this measure instead of dx. So we will consider our standard heat equation. This is Neumann boundary condition. This is initial data. So we know that this particular evolution problem, if you feed non-negative initial data, your solution also stays non-negative for all time. So that is true for this equation, and it also has this conserved quantity, in the sense that if you integrate this equation in the x variable, because of this Neumann boundary condition, this Laplacian term, it will just vanish upon integration over x variable. So you will find that the time derivative of this quantity is just 0. So essentially what we have shown is this quantity is conserved a long time. For every time t, this is just the mass, right? So the total mass remains constant with time. Is there a question?
No. People are entering. So
okay. Oh yeah, sorry about that. Okay, so this mass is conserved. So the take-home message from this slide is there is this evolution problem whose solution satisfies this conservation property, that the total mass is conserved. Okay. Now, this conservation property should also carry over to that equilibrium state, whatever that may be. Right? So now let us introduce this quantity. You give me any function v for whom I can make sense of this integral. So that integral is just a constant. So v bar is my notation for that. It's just the average, right? In this case, because I have taken the measure of omega to be 1. So the average of this function v is just denoted by v bar. And from the previous slide, what we have seen is, if I take the solution to my Neumann heat problem and I average it in the x variable, it is independent of time. It has got a value which doesn't change with time. It's the same average that you start with initially. Okay. So that is from previous slide. Now let us define a functional E Okay, so this functional acts on this fellow u in this, it's defined like this. It's just the difference between u and its average u bar and squared, okay, and integrated in the x variable. So this you can make sense of any function u, right? For any L2 function, you can define this quantity. We are going to consider this functional E acting on the solution of this Neumann heat problem. And then we are going to differentiate in the time variable. So we are taking the time derivative of this quantity. So you take the time derivative inside the integration, and so you just do the thing. So u bar, we have just observed in the previous slide that this is a constant, right? So you will just get 2 times this quantity times the time derivative of u. Now, at some point, we have to use the fact that u is the solution to this problem. So solution to the heat equation. So the time derivative of u is just replaced by the Laplacian of u. And then you do an integration by parts. You throw this one of the derivatives onto this guy, and u bar is constant. Just keep that in mind, and you get negative. You know, the negative comes because of the integration by parts, and you get the square of this. So essentially, you have got a non-negative quantity multiplied by a negative sign here. Okay, so it's non-positive. So we have essentially shown that this E, this functional E, it's a Lyapunov functional for the heat equation. So there is a flow for your evolution problem along
Harsha?
which, yes, yes,
U bar, u is a function of t and x, and so u bar in your definition is
function of T, but that is independent of time because of this conservation. Because
the integral, yeah.
Yeah, the integral of u, it stays
Yeah.
constant with time
Okay.
because of the Neumann boundary condition. When you integrate the equation, the Laplacian term does not contribute anything. So you get d by dt
Okay.
of the
Okay.
integral of u is 0.
Okay.
So
Okay.
u bar turns out to be independent of time as well.
Yeah. Okay.
So,
Thanks.
so you this, and so essentially in this slide we have shown that if I evaluate the functional E on the solution to this Neumann heat problem, its time derivative is non-positive. Okay, so that's what we have shown. And so in the dynamical systems theory, in dynamical systems, when you find such a thing for a solution to your ODE, you call such a thing as a Lyapunov function, right? And so this E is a Lyapunov functional on the heat flow, on the Neumann heat flow. So that's what we have shown here by this simple computation using integration by parts. Okay, so we have shown that d by dt of E of u is less than or equal to 0 because this is integral of a non-negative quantity. Okay. Now, the next stage is we are going to use a functional inequality. Okay, so I hope all of you are familiar with this notation h1. It is just a collection of all those functions which are square integrable, and their derivatives are also square integrable. There is this little notion of weak derivative and all. Let's not bother about it. So this Poincare inequality, it essentially says the following: you take any candidate from this space h1, okay, then there is this constant, universal constant, which depends only on the domain omega. It doesn't depend on the function that you picked. And this inequality holds. You take the difference of f from its average, f bar, the average from the previous slide, okay? F minus its average squared and integrated over omega is bounded from above by this universal constant times the square of the gradient of f integrated over omega. So this is the Poincare inequality. Okay, so now why are we invoking Poincare inequality here? Recall that this first equality, we did it from the previous slide, right? Just by differentiating the functional and using the equation followed by integration by parts, we got this equality. Now, let us apply Poincare inequality for u. okay, as a function of the x variable for every time t. So this fellow acts as an upper bound for the square of f minus f bar integrated over x, right? So, but there's a negative sign here. So the inequality gets flipped and you get minus 2 upon the 2 which is here upon the Poincare constant. The C of omega is called the Poincare constant times the integral of the square of u minus u bar. Okay, but what is this quantity? This exact same thing we had called as that functional E, right? So I'll just this is just the definition of E. So at this stage, we have to invoke the Groundwall inequality. We have just shown that time derivative of certain non-negative quantity is less than or equal to some constant times the same quantity. So you can apply Groundwall to get this decay. So this is just a consequence of the Groundwall inequality. It says that E of u at any time t is less than or equal to exponential of minus 2t upon the Poincare constant times the the functional evaluated initially. So this is convergence to equilibrium. Okay, the equilibrium here is u bar, that constant. So from a physical point of view, what is happening? You have got a plate, let's say, a 2D domain, and so you start with some initial temperature, and you have got Neumann boundary condition. So you are not letting anything leave the domain. Okay, so and you start with some initial temperature and you let time evolve, it is becoming a constant temperature plate. A plate will essentially attain constant temperature in large time. So that's what we have shown using this thing. Okay, so and E essentially is measuring the L2 distance, right? That's how it is defined. So let's just keep this in mind. So the way we did it was we introduced some functional which acts on the solution to our evolution problem. We showed that the time derivative of that functional evaluated along the solution to this problem is a Lyapunov functional, and that right hand side, whatever the time evaluation, the time derivation equates to, that we related back to the functional using some functional inequality which turned out to be the Poincare inequality here. And then the last step was the Groundwall lemma. The key, the main importance of this approach is if we use such an approach, the constants that appear in your decay estimate, they're all going to be explicit. For example, the Poincare constant is explicit for a given domain. So you will be able to say exactly what's the rate of convergence. Unlike, when people studied convergence to equilibrium, in some other earlier techniques that are known are quite popular themselves as well, are this linearization technique. So you take an equilibrium state, you linearize your problem around that state, and then use some spectral analysis to say something about it. But here, the approach is slightly different. You look for some entropy functionals, and okay. So I hope this was clear. So next we do one more example. So this is heat equation, but now we change the boundary condition. We are still in the linear case. Okay, this is the Dirichlet problem. We are now taking u to be 0 on the boundary of the domain. Again, we are feeding some initial condition. So in this problem, see earlier in the Neumann boundary case, boundary value problem case, we had shown that this quantity integral of u in the x variable was a constant in time. But for the Dirichlet problem, this is not true, because you simply do the same exact thing that you did earlier. You integrate the equation, you get time derivative of this quantity. But now when you do integration by parts in the term involving the Laplacian, you will get this Neumann boundary condition, which is not 0, right? So the time derivative does not vanish, so you cannot claim that this is something that is conserved. But the equilibrium state for this problem is 0. And this you can think physically, the intuition is as follows. You are keeping the temperature at the boundary to be 0, and you are feeding some temperature, you're starting with some temperature to begin with. And as time progresses, everything will just cool out, because you have essentially kept the outer boundary to be 0 at 0 temperature. So the equilibrium state is 0. So we need to answer this question. How does this solution, okay, for any initial data u naught, how does it approach 0 as time goes to infinity? Does it decay exponentially fast or does it decay otherwise? Okay, so here, with what rate does it decay? So here you can do the energy method where you simply multiply the equation by u and you can actually show that the L2 norm decays exponentially fast using the Poincare inequality with the 0 Dirichlet boundary condition. But here I am trying to use another approach. Okay, this is because it will be used in another problem later on. And so let us consider, like before, let's consider a functional. And the functional that I'm defining is here. So E of u is defined to be u times natural log of u upon u bar. Okay, so u times natural log of u upon u bar. So that's what u bar is a function which is independent of x at least. We don't know whether it's independent of time. We don't know that. So next we are going to differentiate this functional in time. Okay. So when we differentiate this functional in time, you will get this quantity. Okay. So you may be wondering that, there is, when we differentiate this fellow, that u bar is not independent of time, but trust me, because it's u upon u bar and we have assumed that the measure of omega is 1. Okay. And u bar is just the average of u, it will cancel. So now you will be left with this. It's 1 plus natural log of u upon u bar times the time derivative of u. And now you use the equation that u is the solution to the heat equation. You replace time derivative of u by the Laplacian of u, and then you do integration by parts. This is just a constant, right? When you throw the derivative onto the logarithmic term, you will just get 1 upon this guy times the gradient of this guy, gradient in the x variable. So you will get gradient of u square upon u. Okay. Now this quantity, gradient of u squared upon u, is what? It can be rewritten as gradient of the square root of u whole square. Okay. So that's just a rewrite, but with a factor of 4. Let's just keep this in mind. Again, we have done the following. We have shown that the time derivative of this functional has got a sign. It is less than or equal to 0, thanks to this integral being non-negative. Okay. Now we have got that E is a Lyapunov functional again. Now what is the functional inequality that we are going to use? So here is the functional inequality. It's called logarithmic Sobolev inequality. It says the following. You take any positive function f such that f dx is a probability measure. So when you integrate f over the domain omega, it's equates to 1. Then integral of f log f is less than or equal to, again, some universal constant which has nothing to do with the function but the domain, times the square of the gradient of the square root of f integrated over omega. Okay, so this is called the logarithmic Sobolev inequality. It can be derived, okay, from the classical Sobolev inequalities. Okay, so f log f is bounded above by this. Now you must be thinking, okay, so applying this here, see, we have shown that d by dt of E is equal to that. So we can upper bound this negative of 4 times this guy, thanks to this logarithmic Sobolev inequality. Okay, by if I apply, this quantity, if I take f to be u upon u bar, okay, it integrates to 1 thanks to the definition of u bar. Okay, so u upon u bar is it integrates to 1 and it is strictly positive. If your u naught is strictly positive, it is non-negative, your solution will be strictly positive. So you can apply logarithmic Sobolev inequality, and so in place of f, I have simply taken u upon u bar, and you get this. Okay, u logarithm of u upon u bar dx is bounded from above by c of omega times this one. So you must be wondering what happened to the 1 upon u bar here. See, here you don't have u bar term, right? So f is taken to be u upon u bar, so that also comes out here. So there is a u bar term here, so they both cancel each other. So Everything is fine. So applying logarithmic Sobolev, you get this. So now you are in the game. So let us combine all the three. So we had d by dt of E is this, then this fellow acts as an upper bound for the same quantity, which is just E. So combining all these things, you again are able to apply Groundwall lemma on this non-negative functional E. Okay. So d by dt of E of u is bounded from above by minus 4 upon C of omega times E. So you get convergence to equilibrium exponentially fast. Okay. So now this fellow, this convergence, it's called convergence in entropy because it's only in the f log f term, right? So you got u log u minus log u. Okay. Now, can we say something about the convergence in LP distances? For that, there is another functional inequality which is called the Cesar Coolback Pinscher inequality, which essentially says the following, which says that you give me two non-negative functions f and g, both are in L1 and their L1 norms are 1. Yes?
Harsha,
Yes.
if you go back to the previous slide, yeah, so this rate of convergence for the, so there is exponential decay to 0, right? So this rate of convergence, the constant depends on the constant, the log Sobolev
Yes, yes.
inequality. But if you were to do it like more simply, like if you were to like just do the eigenvalue expansion for the Laplace operator,
Yes.
then you would
There
get the
you
first
get the first non-zero eigenvalue of the
for
Dirichlet
Dirichlet.
Laplacian. Yes.
So that will be like the inverse of the Poincare inequality.
Yes.
So how does it compare? Meaning you get two different rates. So which is better? That do you know?
Okay,
Like
okay. So this I don't know off the top of my head, which will
yeah,
give the better constant.
yeah,
Okay.
yeah,
So this I don't know right now. I can tell you
yeah,
maybe later. Okay. But you
yeah.
are
Okay,
absolutely
sure.
right. There,
Yeah,
you are essentially getting convergence in the L2 norm
yeah,
because there you are using L2 setting. And
yes.
you get, you're absolutely right, you get 1 upon
Mm,
the first
mm,
eigenvalue of the Dirichlet
yeah,
Laplacian there. Yeah,
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 thanks for
sure.
that. So I'll,
Yeah, in
I'll
any case, in any case, I think yeah, the energy here is different. So this is a rate for a different energy. Yeah,
yeah, this
sure.
is, yeah,
Yeah,
something different
mm,
is decaying here. Yes.
yeah, yeah.
So,
Okay.
Rajesh, but doesn't it similar? Because you get lambda 1 equal to grade u by integral u square, right? It will be somewhat similar, which is similar to the Poincare inequality, right? Isn't it so?
yeah, I mean, you
Uh,
see, this one in the log Sobolev
Well,
inequality,
yeah, that is true, but lambda 1 is also equal to integral grade u square by integral u square, where u
integral u
is
square,
the
but here you have got,
eigenfunction.
yes, yes.
Oh, this C omega corresponding to f log f.
F log F.
That
Yeah,
one.
so that's why. Yeah, so
So
these
that's
constants may not be the same. I
yeah,
don't
that
know.
constant, yes, f
Yeah,
log.
yes.
All right. Okay.
Okay. So this convergence, but now this is just telling you that this quantity E is decaying, right, with time. Now, can we say something about the LP? No. Okay, so for that, this Cesar-Coolback Pinscher inequality comes to help. This inequality says the following. You give me two non-negative functions f and g which are in L1 and their L1 norms are both equal to 1. Then the square of the L1 norm of this difference can be upper bounded by twice the integral over omega of f natural log of f upon g dx. Okay, this is what Cesar-Coolback-Pinscher inequality says. Now, we have just shown that this quantity, E of u, right, E of u, which is u log of u upon u bar, this decays with time exponentially fast for u being the solution to this problem. So now let us relate that E back to some other norm. So here in the Cesar Coolback Pinscher inequality, if I take f is equal to u upon u bar and g is equal to this constant function 1, then I'll just substitute here u upon u bar and g equal to 1 and then do the algebra. Okay, so the 1 upon u bar comes out is less than or equal to 2 times u times log u of u bar, which is essentially e of u here. So this is what we had. We had got that this right hand side is decaying exponentially fast. Now, thanks to this observation, we are able to say that u is converging to u bar. Okay, L1. This is the L1 distance. Okay. Now, this is the recipe, right, that we have seen. We will first identify conserved quantities. It kind of helps us to identify the equilibrium states. Okay, when we identify those conserved quantities, then we have to introduce a Lyapunov functional, which is in this theory it is referred to as entropy. Okay, associated with the equation, and then you show that it is not increasing with time. So time derivative of E of u, where u is the solution to your problem, is negative of d of u, where d is called entropy dissipation. That's just a name, where d is non-negative. So with a negative sign here, so it becomes non-positive. So it's not increasing with time. Then we have to relate the entropy with entropy dissipation. In the 3 examples that we have seen, we have related this entropy and entropy dissipation via certain functional inequalities. And once we have got this relation, we can go back to this, time derivative equality for the entropy and get an inequality, differential inequality, which is suitable for applying Groundwall. Okay, so that's where we are at. So this is the recipe for entropy methods. Now this is a question of interest. This is not known, by the way, and one of our colleagues in IIT Delhi, Srinath, they recently proved that this fractional heat equation. Okay, so this is fractional in space. So this is posed in a bounded domain. So, in case of all these fractional problems, you need to make sure that in the complement of your domain, your u is 0. Okay, that's how you impose boundary conditions here, because this is a non-local problem, because you need information from everywhere else. So now u0x is just u0, some initial data. So where s is some parameter. They have actually shown using some classical spectral theory methods that the equilibrium state for this problem is also 0, that this fellow converges to 0, but they have not shown any rate of convergence. Okay, it's not known. And can one apply this entropy methods approach to get a decay rate for this problem? So this is an open question. Okay, so what's the entropy for this particular fractional heat equation? It's not known. Okay, so if any of you are interested, you can try this. The Srinath and company's paper, it appeared a year ago, I think, where they have actually shown that the equilibrium state is 0 and the convergence happens, but they don't talk about the rate of convergence. Now, here is another example. I'm sorry, this is again linear. We'll get to the non-linear.
Harsha?
Yes.
The previous problem, so if you use the same setup as linear thing, and there are many definitions of the fractional Laplacian. So if you take the fractional Laplacian here to be defined through the spectral decomposition, then you can immediately get a rate of convergence in terms of the eigenvalue of the Laplacian itself. So that is easy. So but it depends on, so if they've chosen not the spectral definition, then
but
maybe
this non-local integral definition.
Yeah.
Then that's their approach actually.
Yeah.
But I don't know what is the corresponding entropy functional if you are working with those non-local integrals.
Sure.
Oh, thanks for that point.
Yeah.
So now let us switch gears a little bit. Okay, so this is called the Fokker-Planck equation. So Fokker-Planck equation is motivated by SDEs, okay, stochastic differential equations. So if you are not familiar with SDEs, don't worry, it appears only in this slide. So if you have got some random variable which satisfies this stochastic differential equation where this W is a Brownian motion, and so now the corresponding probability density. So this random variable has got something associated with it. It's called the probability density. Let's denote it by P, and that satisfies a partial differential equation. So for us, this is the starting point. Let's say if you're not comfortable with this, so that P satisfies this particular differential equation. It's called the Fokker-Planck equation. Okay, so it's divergence of x times P plus gradient of P with respect to the x variable. And again, you start with some initial data P naught. Now, the question that we want to ask is it possible to employ an entropy approach where you find some functional, find its time derivative, show that it's non-negative, non-positive, and then relate the entropy with entropy dissipation and apply Groundwall. So those three steps, can we do it for this problem? So here, first of all, let us see whether there's any conserved quantity. This is in a divergence form, right? So there should be something conserved here, and that's the integral of this P. If you blindly integrate this equation, you get d by dt of P, which is equal to divergence of this guy. And you are assuming that this P is integrable, so all these things will die out at infinity. So when you differentiate, when you do integration by parts, you get 0. Okay, so you get the time derivative of this is conserved. So if you call this the mass, so the mass is conserved at every time t. So now the equilibrium state for this problem, for this, you want to find some function, let's call it P infinity, which vanishes on this operator. Okay, so at first glance, it's not very clear, but this is the guy which vanishes, okay, which makes that operation vanish. So m of x, which is the centered Gaussian. And so in order to see why that is the case, you will, let's just, this is a simple manipulation. If you have not done it before, it looks like really very surprising. Okay, so this is what we are looking at. We are looking for a P infinity which satisfies this equation, right? E0 equals divergence of x times P infinity plus gradient of P infinity. Now, let's just rewrite this parenthesis, the term in the parenthesis here, the one whose divergence we are taking, as this one. It can be rewritten as this m of x, which is the centered Gaussian, this bell curve, exponential minus x square upon 2. This is just a normalization constant. When you integrate this over RD, it is simply 1. And m of x times gradient of P infinity upon m of x. I implore upon you to just do this calculation. This is simply this guy, x times P infinity plus gradient x of P infinity. So now you are taking divergence of, this is some non-negative thing, right? M of x times gradient of this. So for this P infinity to be a solution to this problem, this P infinity should be a multiple of m, some constant multiple of m, so that this gradient of the constant will just vanish and give you 0. So that's the idea here. So P infinity, the solution to this problem, thanks to this little observation, you can say that the equilibrium state should be some constant multiple of the centered Gaussian. Okay, so, and that constant, thanks to this conservation property, should be equal to the initial mass. That means this quantity, the integral of P0 over RD. Okay, so that should be that constant. So that is the equilibrium state for this problem. So this is the candidate which will make this right hand side vanish. Okay, so now we want to know, if I start with any initial data P0, will I converge to this guy C times M? And if I converge, how do I converge? Okay, for that in order to define the entropy function, we are going to take a similar, P log P kind of entropy functional. So for that, let us make this one more kind of change of variables, change of unknowns, let's say. Instead of working with P, we are going to work with Q, which is simply P upon P infinity. P infinity being constant times that centered Gaussian, you can divide by P infinity. So Q is just P upon P infinity, and because P satisfies the differential equation, P infinity satisfies that right hand side, right? You can do the computations and you can show that Q satisfies this equation. It's kind of an advection diffusion type problem. And for this one, now let us define this entropy first of all. P log P upon P infinity. It is similar to U log U upon U bar, the one which we had used for the Dirichlet heat problem, right? So you take P log P upon P infinity, and because of this definition, what is this fellow? This is simply, what is P? P is Q times P infinity and log of Q. That's all this is. Now let's take the time derivative of this. That's our first step, right? After defining some entropy, you take the time derivative. I differentiate this quantity now, which is just an equality. So I get time derivative of Q times this guy times P infinity. Now I replace time derivative of Q by this right hand side, Laplacian of Q minus X dot gradient of Q. That's all that's happened here. Now when you throw the derivative onto this guy, there are two terms here, the one in the parentheses and the P infinity. P infinity is not a constant, it also depends on the X variable here. So when you do the integration by parts, when it hits this, you get the gradient of square root of Q whole square, similar to what happened for the heat problem, Dirichlet heat problem. And when you do the integration by parts, when it hits P infinity, like magically, the term which you get will be of opposite sign to this exact same term, so it will just cancel. So you will get some, again, the time derivative is non-increasing, it is less than or equal to 0. So that you will be able to show. Then there's a version of log-Sobolev inequality. Okay, I'll not get into the details here. Now, instead of the dx measure, you will be working with P infinity dx measure, which is a probability measure, and Q log Q is bounded by this. And again, the same story. Because this with a negative sign has come as an upper bound, is in the time derivative of the entropy, right? So you relate those two to get this, and then you apply this Groundwall lemma, and then relating this entropy again with the L1 norm, you can, Cesar Coolback inequality, which says that the square of the L1 norm is bounded from below by some P log P term, and you will get convergence. Okay, so that's that. So far we have seen only, linear problems. How about nonlinear problems? Can this method also use nonlinear reaction diffusion equations? I'm sorry, I'm running too slow here. Sorry about that. So here is a nonlinear reaction diffusion system. We have got this is a system of equations. Okay, so we have got two components, U and V, and so U satisfies this reaction diffusion equation, and V satisfies this one. So this is coming out, I mean, these rate functions which are sitting as the right hand sides, they are modeled out of this chemistry. Okay, there is a chemical quantity A which acts with itself to give you B, and the B disintegrates to give you back to A. It's a reversible chemistry, and if you write down the rate function, it will have this particular structure. So, and again, you are giving some non-negative initial data, and we are working with Neumann boundary conditions. So first of all, let us see, are there anything conserved here? The first thing to notice is, in all this reversible chemistry, you can actually add certain equations to make the right hand side 0. So in fact, if you multiply the second equation by 2 and add the two equations, you will find that this right hand side simply vanishes, and so you will get u plus 2 times v integrated over omega, that is conserved in time, because you have got this Laplacian terms. When you do integration by parts, you will be encountering the Neumann derivatives, which are zero by assumption. So in this, for this particular problem, this quantity is a conserved quantity. So if you start with some initial data u0 and v0 such that this is some m, it is m for all time t. Okay. Now, so that same thing. So let us now consider equilibrium states which are constants. Okay. So let us take u infinity and v infinity to be constants. So this particular thing should also hold at infinity as well. And we are working again with, domains of measure 1, so that annoying measure of omega doesn't bother us. So this should be m, and at equilibrium, right, this should also vanish, because the constants, this will vanish, but this right hand side should also vanish. So u infinity square should be equal to v infinity. So we have got this. Now we
can I see the slide previously?
Yes.
Don't you get, if you multiply the second equation and add these two equations for u plus 2v, it becomes a linear equation?
For u plus v.
No, you multiply by the second equation by 2 and
add, you will get u plus 2v.
Your whole non-linear term will get vanished.
Yeah, the non-linear term goes away, but that's
then
not an.
You will get a linear equation for u plus 2v.
No, you will not get an equation for u plus 2v, because the time derivative, I agree with you. You will get time derivative
you
of
have
u
this
plus 2v.
d1 and d2 plays a role.
Yeah, this d1 and d2 are not the same. So it will not be the Laplacian of u plus 2v. So we cannot treat it as an equation for this new unknown u plus 2v. Yeah, that's a good question, but we are not assuming that d1, d2 are the same. If it was simply a Laplacian here with d1 and d2 equal to 1, you are absolutely right. You can just get rid of the nonlinearities and work with u plus 2v here, but not in this case. d1 and d2 are not same.
What is d1 and d2 represent?
They are diffusivities. They are diffusion constants. So from a physical point of view, the diffusion constants of various species, they differ. They will not have the same diffusion constants depending on their molecular size and all. So this is more realistic to take diffusion constants to be different for different species.
Now the interesting thing why I ask this is your conserved quantity is still u plus 2v.
Yeah, it is still u plus 2v.
And d1 and d2 is not playing a role there.
Yeah, they are not playing the role for the conservation. But it so happens that in all these reaction diffusion systems, when you take different diffusivities, I mean, the model that we are seeing, the existence is known, existence uniqueness, global in time. But it's an open problem to show for a general reaction diffusion system with different diffusivities, global in time existence. It is not known until now.
Okay.
Yeah. And the difficulty mainly arises due to these different diffusivities. Okay. So now, if we are looking for constant equilibrium states, you have to send your equilibrium states should satisfy these relations, and then you are you are in the realm of quadratic polynomials. You just take v infinity is equal to u infinity square. You solve for u infinity, you get this, and once you have got u infinity, you can solve for v infinity here. Now, what is the function? So let us try to kind of come up with a similar strategy as before. We will introduce a functional e, which is in this case, this is the definition, u log u minus 1. This is u log u minus u, and this is v log v minus v. So if you are worried about this is being non-negative, you can just add some constant to this. Okay, u log u minus u plus 1 is always non-negative. Okay. Similarly for this. Now, before we time differentiate, let me just show one little computation here. So we will show that this is called relative entropy. This is the entropy at time t, right? E at uv, and this is entropy at infinity. That's the equilibrium states. In fact, this difference is known as relative entropy, and we have simply written down what is this difference here. Okay. That's this line and this line. And then we have simply added and subtracted certain things. Okay, so also it comes out to this relation. It comes to this form. You must be recalling now. It's of the form u log u by u infinity, and this is v log v by v infinity. And we know how to relate these guys back to the L1 norm square, right? So that's the Cesar Coolback inequality. And this term, okay, minus this term can be lower bounded thanks to Cesar Coolback inequality by the L1 norm of the difference between u and u infinity and the L1 norm of the difference between v and v infinity. So just remember that we have not shown that the time derivative of this particular functional is decaying with time. We have not shown that yet. We have just made this observation that the relative entropy can be bounded from below by these quantities, the L1 norm of these differences. Okay, let's just keep this in mind. Now we do our favorite thing, time differentiating the entropy. So you time differentiate that u log u minus u and v log v minus v terms. You get this. Then you use the equation, time derivative of u, you replace by d1 Laplacian of u, the right hand side, and dtv is replaced by this. Then you do integration by parts in the Laplacian terms. Okay, like before, the log term will give you a u, and this you can rewrite as gradient of the square root of u squared with a coefficient of 4. This trick we had done last time, whenever we had the log u as the multiplier. So these two terms will give you these two terms, and if you regroup the reaction terms, you actually get this term, which now, because this is of the form a minus b log of a upon b. Okay, a minus b into log of a minus log of b, that is greater than or equal to 0, right? So this is greater than or equal to 0, but it has got a negative sign here. These are all integrals of non-negative quantities, but they both come with negative signs. So we have essentially shown that the time derivative of this entropy functional is less than or equal to 0. Okay, now, and so let's just recall this. Okay, so this is an algebraic identity. X minus y times log of x minus log of y is greater than or equal to this particular constant, 4 times the square of root x minus root y. We are going to use this. Okay, and this is just a notation. We had this lot of square roots, right? Square root of u and square root of v. We will denote it by capital U and capital V. So we have essentially shown, this right hand side without the negative signs, we are going to define them. That's the entropy dissipation. We are going to give a name. It's this term plus the gradient V term and this guy. Okay. Now, we know Fokker inequality we have seen already, right? So this square of the gradient of u can be lower bounded, okay, can be bounded from below by 1 upon the Poincare constant times the L2 norm squared of the difference of u and its average. Similarly, the square of the gradient v, okay, because we are just lower bounding this. And now this is of the form x minus y log of x upon y. So that algebraic identity that I wrote, that I have used here, you get this. So now what have you shown? We have shown that duv, which we have defined here, that came with a negative sign in the d by dt of e term, can be lower bounded by these quantities. Now, by some algebraic manipulations, you can actually show that you can relate these guys again to the entropy, relative entropy, E minus E. I am not showing those calculations. I'm sorry about that. Okay, so now putting it all together, so we have, please remember that, okay, trust me when I say that after some manipulations, we can actually improve this, replace this lower bound by the relative entropy. So that cuts it, right? So we have d by dt of E is equal to negative of this d, and that d is lower bounded by this. And E of u infinity v infinity is just a constant, right? you can time differentiate this and that is 0 because you are simply integrating constants and that is 0. So you will get that the relative entropy decays in time, and now relative entropy can be related back to L1 now thanks to the Cesar Coolback Pinscher inequality. So you will get convergence in L1. Okay. So are there any questions until now?
So far, no. Please go ahead. You
Okay.
have very less time.
Yeah,
So
sorry about
maybe,
this, guys. Sorry.
yeah,
I will
no
quickly,
problem, no problem.
yeah, quickly go through. Okay, so uh, that is all in the context of the classical problems which are there, and this method of entropy has been used heavily recently in kinetic theory. Okay, so these are the two founders of kinetic theory, if you may. And in kinetic theory, it's all about collection of large number of particles. Okay, so we know from classical mechanics that when you have particles, you try to study their position and velocities and how they move and all those things. But if you use Newton for each of these particles, where there are so many of them, it becomes very tedious and almost impossible to study. So for that, what people do is they study something called the particle distribution function, so which is denoted usually by f. Of t comma x comma v. So you have got your position variable, which is the x variable, and the velocity variable, which is the v variable. So the physical meaning of this particle distribution function is, if I take an element dx dv and multiply this particle distribution function, whatever number that I get, it kind of gives the density of particles in that volume element at that time t. Okay, so that's the meaning of this function. And you can associate. In fact, we can never measure the probability, that particle distribution function, that we are unable to measure. Okay, the things that we can measure experimentally are this local density, macroscopic velocity, temperature. These are the things that we can measure, and these things, the measurable quantities, are related to this particle distribution function via these integrals. Okay, there are these relations, and Maxwell and Boltzmann, they first wrote down the equation for particles, particle distribution functions of a collection of particles which are evolving by binary collisions. Okay, so two particles will come, they collide and move on. So anyway, let me skip this thing. Okay, this is free transport. I'll show you the Boltzmann equation. So this is the Boltzmann equation. So you have got transport. Okay, v is an independent variable here. Okay, unlike the very first PD that we saw, where a was a constant, so v is an independent variable, and q of ff, so that's just a notation for this integral term. So this Boltzmann equation, which was written down by Maxwell and Boltzmann, so this is this. It is for that distribution function f. It is, at a first glance, it looks too complicated, but once you get used to it, it's fine. And this is a quadratic nonlinearity. Your f is multiplied by itself once. Now, that fellow has also got some conserved quantities and so on and so forth. I'm sorry because I'm rushing, but okay. So maybe I will explain this and I'll stop. This entropy that we saw for various equations, Boltzmann himself found the entropy functional for this integral equation, the one which he wrote down, and he is known for that. Okay, it's called Boltzmann's H theorem, and he called his entropy functional, he denoted it by H, and hence it's called the H theorem. So he showed that if there is a solution f to this Boltzmann equation, okay, and I define this functional h, which essentially integrates this quantity f log f over velocities and space. He showed that the time derivative of this quantity is, negative of some positive quantity. So like we have done for various examples now. So his calculation was quite like what we have been doing. So you time differentiate, you take the time derivative inside, you use the equation, okay, but you get this, right? So his genius was to show that this fellow has got a sign, Okay, so and he showed that this is negative of some integral of DFF, where DFF is this fellow. Okay, this another integral, but the main point that he showed was that was greater than or equal to 0. So this h acts as a Lyapunov functional for the Boltzmann equation. So this is f log f integral. Okay. Now you want to take it some furthermore, right? So d by dt of h of f is this. So this was shown by Boltzmann, and he, like, if there is a stationary state, it should necessarily vanish on this. This dff should vanish for that stationary state, and one can show that the stationary state for this equation should look like this. It is again the exponential of some guy minus this guy, where this rho t u are functions of x variable. But because your equation has also got the transport term, v dot gradient x term, it will kind of push these constants to 0. It will require that all these constant, these functions rho t and u, they are all constants. So you have got these equilibrium states which are called the Maxwellians, and Head's theorem, it said this, right? But then you ask this question: if you want to get a rate of convergence for this h functional, you have to relate that d with h, right? In order to use Groundwall type argument, and that's the context of a conjecture known as Chercheniani's conjecture. Okay, so in order to relate back d with h, sorry, and in the case of the heat equation and various examples that we saw, that relating entropy and entropy dissipation, that was being done by functional inequalities. Okay, so and Chercheniani's conjecture is essentially asking for, is there this kind of inequality? Can the dissipation functional can be related back to this h functional via some linear function psi? Okay, and this was conjectured by Chercheniani, whom you see here, and this was, I mean, like, there have been some counter examples, because you see there are a lot of parameters involved in this Boltzmann equation, right? And so there have been some counter examples, but Cedric Villani was able to prove that, okay, maybe it's not linear, but you can get as, I mean, you can make epsilon as small as possible, but it's not linear. Okay, but as you can see, linearity will give you exponential convergence. If you see anything non-linear, then there is trouble. Okay? You will not get exponential decay. So I'll give you some references towards the end. So this is called Chercheniani's conjecture, and okay, and that has been resolved almost. Okay, so there have been some very good survey papers I'll cite at the end. So with one of our students here, we asked the following. Okay, this is final 2 minutes, Ravi, I will finish. Okay, so we asked the following. We take this equation called the Bhatnagar-Gross-Krook equation. It's called the BGK equation. We throw in a coefficient here. So far, there have been some right-hand side terms which are pushing things to equilibrium, right? So now we take this coefficient which can vanish in certain parts. So, and then we ask the following question: does the convergence to equilibrium take place? And if it converges, what's the equilibrium rate, and rate of convergence, and so on. So, skipping almost all details, what we managed to show is that no, there are certain configurations. This is inspired by the Bardos-Labo-Rausch condition from control theory. The way we built these coefficients, we managed to show that the solution f converges to, I mean, the rate at which this convergence can take place can at most be 1 upon square root of t. So there is a lower bound of c upon root t kind. So you cannot have exponential convergence in this problem. When you have degeneracies, you are essentially turning off the right hand sides in certain parts of your phase space. Okay, so I'm sorry I could not get to this. And here are some references. So there is this very nice, kind of introductory note which was written by a bunch of people who, Anton Arnold, and I think that paper has got like some 10 authors. okay, from 2004. Entropy method is beautifully explained there by taking various examples. If you are interested, you should look at that. Then the nonlinear reaction diffusion example that I took, it's from Laurent de Villette and Fellner from 26. When it comes to convergence to equilibrium, the very big result for the Boltzmann equation is due to de Villette and Villani. And the Cherchiniani's conjecture, if you are interested, you should look at this paper from 2011. And there is this topic of hypocoercivity. Okay, this is related to hypoellipticity of uh, Hormander. There is this nice memoirs from 2009, and the construction that we have done for the BGK equation was inspired by the linear Boltzmann equation, which was done by Bernard Salvarani. If you are interested in learning more on Boltzmann equation, these are the two books of Cherchiniani and co-authors. So you are welcome to read that. Okay, with this I stop, and my sincere apologies. I ran out of time. Maybe.
Thank you, Harsha. Thank you very much for a nice talk. Let's invite some comments very quickly. Very quickly. We don't have time at all.
Thanks, Harsha. Very nice talk. So, meaning I would be interested in the last thing which you said you've done with the students. So, if you have some preprint, you could please
Yes,
mention.
yes, yes. We will be, like, we're still writing it. We should be uploading it soon. Okay, so maybe in
Okay.
another month, I would say, given the
Yeah.
pace that I have.
Yeah, I
So,
just have one more small comment. So, the thing you showed, um, so this variant where you had this P infinity, the probability thing, like,
okay.
yeah.
Yeah.
So there you have convergence in what space L1 again
Yeah,
for
yeah. So
the,
here you get what L1,
yeah.
because you first
So
show.
if you want, so did anyone do the L2 thing? So it must also be interesting to have the L2 convergence, right? No.
Yeah, yeah. But these are all probability measures, because
Yeah.
you are looking for
Okay. Yeah.
probability measure.
Okay. Mm.
Their L1 convergence is more appropriate in some sense.
Yeah.
Uh,
Yeah. Okay.
yeah, but I don't know if anybody did the LP cases. Uh,
Okay.
yeah,
Yeah.
but here I think their main goal was to look for L1 convergence.
Yeah. Okay. Yeah, yeah, I understand. So no, I was thinking them as like density. No, they are just probabilities. Okay.
Yeah.
Hi Harsha, can you hear me?
Yes, yes, yes.
Okay, so thanks for the nice talk. I have a couple of questions that, okay, the first one is that, um, okay, so you also have that the Liao type inequality, right? So related to the thing what you have presented,
Mm.
that entropy.
Yes.
So can you say anything about the Liao inequality? Um, for example, the Fokker-Planck equation. I mean, for heat equation, definitely we know. For fractional heat equation, we don't know. Or for example, um, like the Boltzmann equations, or like also you presented this Fokker-Planck equation. So do you have any recipe for deriving Liao? Because my understanding is that if you have Liao, which
Yeah.
is a pointwise inequality instead of like that
Yeah, I mean, these
integral over
are
dk,
for. Yes, yes, yes.
then you might have something more, right?
Yeah, but you see, that is for. Yeah, you're absolutely right. These are all very point-wise estimates for the kernels, heat kernels, and
I mean, not exactly hit kernel, but also, I mean, you can do it for the solutions, like for the positive solutions, like relating that derivative with respect to time and x, and
uh,
in a it's
this
kind of
I'm
this
not aware
partition.
of. I
And
thought.
and the thing
Oh,
is that there are also this log appears that partial. I mean, I can tell you for example, the inequality appears for heat, like partial t log of u
mm.
plus grad of log of u, that is greater or equals to n by 2t or something. that again you get a constant which is independent of kind of solution, depends only on dimension, time, something like that.
Okay, okay,
So
okay.
yeah, so that's one thing. And okay, and the another question that's kind of okay, so there is a one technique that people use, that for example, if you have the constant coefficient operator that you have been doing,
Mm.
so you have this self-similar solution, right? So for instance, you can write down the solution. For example, like if you take the heat equation, for instance,
Yeah.
then you can write down a single profile f, which is like f is a function of mod x by t or something, or mod x by t to the power alpha, or 1 by t to the power beta f of mod x to the power t to the power alpha, and then you find out alpha and beta and f. For
Yes.
instance, for heat you get e, that's the time, or like what is the self-similar kind of solution. So, and we know that if we start from heat, we land up with a self-similar solution for the Fokker-Planck equation.
Mm.
Now, so the Fokker-Planck equation and the heat equations are connected if our approach is via the self-similar solutions. So now my question is that there are two. So first of all, do you have similar thing regarding the Boltzmann? Also the time-dependent Fokker-Planck equation.
Okay, for self-similar solutions for Boltzmann, I'm not aware of. Okay, because it's the integral term, it's too difficult to handle. And in the self-similar variables, I don't know what happens to that. I am not aware of it at least. Okay, but self-similar solutions now for the Fokker-Planck equation, you're asking.
Yeah, yeah.
Uh, this. Okay. Mm, stumps me. I don't know, but it must have been studied. This is
I
some
see.
standard technique, but I don't know, man. I don't know. But for Boltzmann, um I'm sure that it has not been tried because it's too rigid an operator. Okay, so there
I
are
see.
not many a priori estimates known. It's too difficult to get any sort of compactness there. And I don't know.
And
Yeah, I mean,
belief,
these
my
questions
belief
are
is
of
that
course
you at the middle of the talk you mentioned about this the fractional heat equation,
yes,
the non-local version of heat. So so you want to also look into that, the non-local version of the Boltzmann, right? I mean, it's not the non-local version, that the collision kernel what you are talking about, which is a
mm,
quadratic thing
mm.
that we want to. So I believe that it has also that the non-local characterization, right? That
Yes,
because it
yes, yeah.
allows the
So
particle to hit or collision from any direction, any point. So like that kernel you want to replace by the fractional kernel, or like
yes,
or
no, no.
some
I
non-local.
mean, what people have realized is this integral operator. It behaves more like this non-local diffusion problems, and
Like
they
I mean,
have,
right, the fractional heat
yeah,
equation you mentioned.
yes, yes, yes. And so they have managed to, you know, get some inspiration from this non-local heat equations theory to apply similar techniques in the Boltzmann world, like Louis Sylvester
I see.
and the company. They have managed to prove certain regularity estimates recently for the Boltzmann equation. They are all very conditional, but they are very much inspired by this non-local theory.
And there, can you specify the Maxwellian, that the entropy state? Like earlier in the examples, we have the specific form of the
Yeah,
that
so
capital
here
M, right?
also for the Boltzmann, because of these conserved quantities, I said that some things are conserved, right? These things
Yeah.
are, time derivative doesn't change. This kind of fixes the equilibrium state. So this rho will be constant, u will be constant, t will be constant. And those constants are related to the initial data that you pick. So this rho will be the initial density, t will be the initial temperature, u is the initial local velocity. So they'll all get fixed. So you've taken initial condition, there are this rho t and u which are associated with it, and then you write down this Maxwellian with those constants.
And
But there we don't see the effect of the right hand side, right? I mean the collision kernel. I mean
and
it solves the
the
heat equation.
this one. No,
It
I mean
looks
the
like
biggest discovery of Boltzmann was to show that this fellow, this guy, this vanishes this quantity.
okay, I see.
That's what I mean. That was his ingenuity. He showed that this actually vanishes. This integral,
I see.
this non-negative integral, it actually vanishes for that choice of f.
Okay.
This max value.
Okay. Thank you. Thank you.
Oh, thank you, and thanks for the interesting questions, most of which I could not answer.
Okay, so let's stop here by thanking Harsha once again. Yeah, thank you so much, Harsha. Maybe we'll see next weekend, next week's. You will not miss next talks.
Yeah. You see, I am talking from the office, right?
Yeah.
From home it is difficult for me to do these calls. That's why I had to travel here. Yeah, thanks for
Okay.
the nice questions.
Sure.
Yes.
So see you next time.
Next week, who is going?
Thanks everybody. Next week somebody has cancelled, so maybe Ranjit will be giving the talk. He's
Okay.
here in the audience, so maybe
Yeah,
he will
I
be
see.
talking on.
Yes. Okay.
So he will talk on homogenization. Yes.
Good.
Okay, and
Okay.
maybe next week Thangavelu will talk. He promised, but I'm not sure he will be talking.
Okay.
So maybe something different from PDE. Then Rajesh will be happy. I don't know. He's very angry. I only do. His claim is only PDE. Okay then.
Okay. Yeah.
See everybody. Bye bye.
See you guys. Yeah.